Our research looks at climate history of the planet through what's recorded in the layers in the ice and glaciers around the world. We're documenting the change of the past and also the change in the 20th century. What we've seen so far, and I think of what should really be of concern to humanity, is what's happening to glaciers in places like right here in Peru, the tropical glaciers. They're all retreating. They're retreating in Africa, they're retreating in the Andes, they're retreating in the Himalayas. In as little as 15 years in some of these places, like on Kilimanjaro, there will be no archive. There will be no history left from the ice. We've worked in 15 countries, particularly in the very high elevation sites in the mountain ranges around the world. And the reason we go to a very high elevation is that we want to be above where melting takes place. We want to have a record of the annual snowfall preserved through the ice archive, the history that's recorded in these glaciers. This will be my 20th trip to Quelccaya, the Quelccaya ice cap. The Quelccaya ice cap is 14 degrees south of the equator. It's in the easternmost section of the Andes. And from Quelccaya last year, we drilled 2 cores to bedrock. This year, we only need 1 year to bring our 2003 ice core records up to 2004. This is the Coricalis Glacier that you see down in the valley here. This is the largest outlet glacier coming from the Quelccaya ice cap. The Quelccaya ice cap being the largest tropical glacier on Earth. And we've been studying this glacier since 1978. And since then, we've been coming back and photographing initially the retreat of the ice, but then the formation of the lake that you see there. And through time, this retreat has accelerated, so recently we've been actually photographing this just about every year to get the change. And in 2001, we actually came up along this lake, and this was not exposed. And in 2002, while we were waiting for the horses, I decided to come up just to look at how fast new vegetation was occupying the new land being exposed by the retreating glacier. And I just happened across this plant deposit. And the date of the plant would tell us the last time this ice cap, Quelccaya ice cap, was smaller than today. So we had it dated in 2 labs, and it dates 5,200 years ago. So that tells us that this ice cap has not been smaller than today for 5,200 years.
Well, we are standing on the summit of the Quelccaya ice cap, an elevation of 18,500 feet above sea level. We see here a 1,600-year record. Each seasonal snowfall that occurs here that does not melt preserves a little part of that history of that year.
No lip.
So it lets us see back into the past.
So one of the objectives here is to document that history, but also to archive some of that ice for the future, because we know that our technology, our understanding will continue to increase as we go into the future. But those archives aren't going to be out in the natural world. One of the really unique things that the ice records is in the bubbles trapped in the ice, which is simply the atmosphere of the past, there is a gas record of the composition of the Earth's atmosphere. So we can extract those bubbles and those molecules that make up the water, that makes up the ice, and we can measure how the climate system has changed through time, and particularly how it's changing in the 21st century. This is the last 1,000 years of annual climate variability from the Quelccaya ice cap. And you can see things like the medieval warm period here in the early part, the Little Ice Age, and the warming in the 20th century. If we look at the ice core record, certainly in the last 100 years, the thing that stands out is the huge increases in concentrations in all these parameters in the last 20 years. And for sure, we as human beings are changing the composition of the atmosphere. I grew up in West Virginia, a coal mining state. I always heard these stories about the canaries the miners would take down. And when the canary died, they got out of the mine. And to me, the tropical glaciers are canaries, and they're telling us the system is changing. This issue of climate change and global warming is a real issue. We're not talking about a belief system here. We're talking about what is and what can be documented by facts and by science. And that we need to look at this and adjust our policy, our way of living, our values based on the idea of sustainability, and that we all need to live on this planet.
So the South Pole Ice Core has a couple of main goals. One of those goals is to get like ultra trace gases. And so the reason this is a good site for it is that it has a unique combination of being very cold because it's so far at the pole, yet has a relatively high snowfall. We kind of talk about the ice in three parts. So the upper part is bubbly ice. Bubbles are clearly visible. Then we have a section that we call the brittle ice. So this is where bubbles are still visible, but they're getting smaller and they're under pressure. So when you bring them up to the surface, they want to expand and crack the ice. Now, once you get below a certain depth, those bubbles have actually all diffused out into the ice lattice. So the ice is optically clear.
Most people look at the gas concentration, they want to know how much CO2 is in the bubbles. But you could actually learn a lot just from the physical properties of the bubbles, how many, how they're spaced, how they're elongated, how they're oriented. Like at certain depths, the bubbles cause the ice to be really brittle, and then at certain depths, the bubbles disappear completely and it just becomes clear ice. So you kind of like figure out different properties of the ice. Here, the ice is really interesting because it's like flowing from upstream. So normally, you see these layers and they're very, very horizontal across the core, I guess vertical when you're looking at it. But now you're starting to see them and they're tilted a little bit or they're kind of kinked over. It's really cool. So you can kind of get an idea of how much the ice is shearing at that depth.
Our portion, we do the chemistry on the ice core. The primary purpose of that is to date the ice core. So you get seasonal changes in different chemicals in the ice for various reasons. And if you can get samples small enough, you can actually see those changes and then count annual layers going back in time.
The core will contain 50,000 years of climate history, and so that takes us through three big time periods. So the most recent, roughly 10,000 years.
We processed down to 734 meters continuously. And when we stopped at 734, that was about 10,200 years or so. So just about to the end of the Holocene.
That's kind of the stable, warm climate that human civilization has developed in. Between roughly 10,000 and 20,000 years ago was the transition from the last glacial maximum to today. So that's about a 3 to 4 degree C global temperature change. And then the period from kind of 50,000 to 20,000 years is what we call a kind of glacial climate, so much colder than today. They're not quite as cold as the last glacial maximum. And it's a period with abrupt climate changes in it.
The primary dating chemical we're using is from sea salt. So we're using sodium and magnesium.
Okay.
Get a beautiful signal that shows every annual layer. We pick up volcanic signals using sulfate. And then that sulfuric acid, which also has an annual signal somewhat, you'll see big increases in it for short periods of time. That's a volcano.
We've tied it to volcanoes that we know absolute dates for, and it matches really well. So
we look at ultratrace chemicals. That infers what the dust was, the chemistry of the dust, and how that changes over time, both the amount and the chemistry of it. And from that you can get ideas about wind patterns going back through time.
When we're looking at the multi-track, so we're looking at the stratigraphy of the core, there we're trying to identify any kind of horizontal irregularities. So we can understand if we're seeing each individual year of snow being deposited all the way back for a continuous climate record, or if there may be small little gaps. While we see irregular layers, none are substantial, but we want to understand that process so that we can learn about where to drill cores in the future.
The outside of the core is contaminated. The outside of our stick is also contaminated, though somewhat cleaner. And then we melt it over as a melt head that is even smaller diameter. And then the outside of that goes to waste. The inside, which is now clean, we analyze. But the ends of the sticks are still dirty. So in that freezer, we sit and scrape all the ends before we melt them. And then we actually melt it in a freezer, but it's just like a convenience store freezer, one of those little stand-ups.
I think we were putting 5 cores in the box, 700 meters, divided by 5, it's like 150 boxes or whatever we can ship back. One wooden pallet fits 8 boxes, and then we put 4 wooden pallets on an Air Force pallet, so that's 32. So we can send 32 boxes on an Air Force pallet, and then one plane can take 2 or 3 Air Force pallets. What's even scary to think about is not how much it weighs, but how much it's worth. That's why we're so careful about every one of those boxes. We put a temperature logger in. We have somebody actually sit on the plane and ride with it back to the station to make sure they keep the plane cold enough. But if you think about how much time and effort and money went into these projects, it's absolutely necessary.
And so this is one way that we can begin to look at not just what the climate changes were, but how they happened. And so it's those kinds of questions that, we're drilling ice cores to help answer so that we can really understand, timescales on decades relevant to human lifetimes and how the climate system interacts and responds, and use these natural climate variations that are big to understand what's going to happen.
One of the best ways to understand the Earth climate system as a whole is to look into the Earth's past and to look at different time periods in the Earth's climate history when greenhouse gases were at different levels. How much of the difference is really explained by the greenhouse gases themselves, how much is explained by other factors. Ice cores are among the best records to answer those questions. We collect ice cores both from Greenland and Antarctica. These are the 2 biggest ice sheets in the world, and the 2 ice sheets that contain really very, very old ice. If we drill down to the base of the Antarctic ice sheet, in some places ice has been recovered that's as old as 800,000 years. And so we drill ice cores to get this ancient ice to look at the record of Earth's past climate.
I had a background in chemistry, and I kind of wanted to get a better understanding of the dynamic system of the Earth. We can learn a lot about the climate by looking at the air and the ice. We can learn about how wet or dry it used to be. We can learn about how cold or hot it used to be by just analyzing what geochemical proxies are in the air or ice.
What you're looking at here behind me is a system that will take large volume air samples that are extracted from the ice. This is a system that essentially is a major step in the processing of samples on their way to getting measured for carbon-14, for getting these answers about questions like the past solar activity.
Just recently we returned from an expedition to the center of the Greenland ice sheet. We were outside of Summit Station, and this is one of the most remote sites in the world. The question I get the most is, how cold was it? The first night we were there, it got down to -40, which is the same in both Fahrenheit and Celsius.
What we have here are boxes of ice cores from our recent expedition to the summit of Greenland. This particular set of ice cores is going to be used for carbon monoxide analyses also. These ice cores will get us back to about the year 1800 AD, so to the start of the Industrial Revolution, and we'll be able to really see the full history of carbon monoxide in the Northern Hemisphere and how it's changed over the course of the Industrial Revolution.
What we're really trying to do is just get a better understanding of the changes that we're observing on the planet. Because this climate change is not black and white. The Earth is a very dynamic system, and we can't study it in place, so sometimes we have to look back at proxy evidence and indirect evidence to gain a better understanding of how the Earth has been changing.
It's very important to understand how the climate system works so that we can predict where it's headed, and so that we can with confidence predict what are the conditions that would cause the system to really spin out of control.
A production of the University of Rochester. Please visit us online and subscribe to our channel for more videos.
My name's Nerilie Abram. I'm an ice core scientist and I work with the British Antarctic Survey. And the reason that I work on ice cores is that they're an amazing way of going back and looking at what the Earth's climate was like in the past. And that gives us information on how the Earth's climate is changing now and how it might change in the future. When you get to a field site in Antarctica, there's nothing there. The people who go to Antarctica and do these sorts of jobs are scientists, but once you get into the field, you're pretty much everything. So you need to build your camp, you become a carpenter, you become an electrical engineer, you're a cook. You have to be able to be very self-sufficient to make the project a success. The drill works on a winch. So when we lower the drill down, we drill about 1.5 meters of ice, and then we bring that to the surface, and we lower the drill back down again and drill the next 1.5 meters of ice. And we keep on repeating that process over and over again until we reach the bottom of the ice sheet. When we drill down through the ice sheet, we're drilling further and further back in time. We drilled an ice core that was 364 meters long, and the ice that we recovered from the bottom of that ice core is over 20,000 years old. This is a part of Antarctica where climate is changing really quickly at the moment, and the temperature has warmed by over 2 degrees in the last 50 years. We're seeing glaciers flowing faster than they have in the past, ice shelves are collapsing. When we cut open the ice, we can see these bubbles of ancient atmosphere that have been trapped inside the ice ever since it formed over Antarctica. And we can actually measure the composition of that ancient atmosphere, and it's through measuring the greenhouse gases from the bubbles in ice cores that we get this clearest link between what the temperature of the Earth has been like in the past and the concentration of greenhouse gases in the atmosphere. And that allows us to have a better understanding of how the climate is changing now and how it might continue to change in the future.
It's a busy, freezing cold day inside the National Ice Core Lab in Denver, Colorado.
We're going to cut gas samples out of this core.
Scientists from Maine to California here to cut pieces of precious Antarctic glacier ice to take back to their labs for study.
We started the Ice Core project in 2005.
With support from the National Science Foundation for a project called the West Antarctic Ice Sheet, or WAIS Divide, lab manager Mark Twickler and a team of scientists, engineers, and support personnel traveled to the bottom of the world to drill out and bring back these ice cores. The goal of the project? To collect and study perfectly preserved records of the distant past.
The unique things about polar glaciers is each year that it snows there, the snow never melts. So you get 1 year of snow on top of the next year of snow. It compresses, so everything that fell out of the atmosphere, dust, salt from the ocean, volcanic ash, is preserved in that ice core.
This particular ice sheet is more than 70,000 years old. The team drilled down more than 2 miles into it to retrieve these cores, which were then flown to the U.S. and stored in a giant 40 below zero freezer here at the Ice Core Lab.
Inside this freezer contains more than 10 miles of ice cores collected from around the world.
Twickler says the ice core's layers are like tree rings, each layer representing a year of weather and snow.
We can tell what the temperatures were. We can tell how rough the oceans were around Antarctica. We can tell how dusty Australia was.
Scientists are keen to study the bubbles trapped in the cores, each a tiny pocket of air frozen in time.
We can measure a variety of gases that were in the atmosphere at the time the bubbles were formed.
Other scientists want to know how ice sheets melt over time.
We don't necessarily have a really good handle on how the ice sheet as a whole will respond in a case of changing climate.
Twickler says this icy blast from the past is helping researchers better understand the mechanics of climate change, and that in turn will help them make better predictions as to what a changing climate may mean for our future. For Science Nation, I'm Miles O'Brien.
I'm working on melting about 2,500 years worth of ice from West Antarctica. This is part of a big national project aimed at uncovering climate history and glaciology in this region. Ice cores are a really great way to look at climate history. They're not the only way, and for certain locations on the Earth, you can't use ice cores. But at the poles in Greenland and on the Antarctic ice sheet, ice cores are a great high-resolution record that allow us to look at hemispheric and global scale climate change. There are plenty of other really good ways to look at climate history. For example, corals, tree rings, lake sediment cores, ocean sediment cores, and every different type of record allows you to address a question in a different way or in a different location.
We are melting an Antarctic ice core for the WAIS Divide project. And here we have the melter system. We come in here every day, 10 hours a day, and melt as much ice as possible.
And it's a way to look at the interactions of the atmosphere, the ocean, and the Earth's surface itself. We're measuring the water flowing by continuously. So we get a dust record and a conductivity record. And both of those things have an annual variation in them. And so in those wiggly lines, we can see an annual signal, kind of like tree rings. And we can't really see that in this ice, but as we look at the chemistry that comes out of the ice, we can see that annual record. Okay. I'm going to turn up the pump. So we have a clean lab where we melt the ice core. The ice is melted from one end to the other on a hot plate. You can hear the sound of the core. It's pretty neat as the ice melts. And the water is pulled through that plate, allowing us to get the inside of the ice core without ever having the outer part contaminate that inner part of the core. For the ice that we're melting today, a single year is about this much ice. And so if you imagine the stuff we're measuring on a really high resolution, through that year we can see changes happening and actually figure out what season these changes are happening. You can reconstruct the temperature of Earth, or the local regional temperature, so Antarctic temperature. You can reconstruct the strength of the winds, or the strength of the atmospheric circulation around Antarctica. We also see volcanic eruptions, and actually today will be melting ice that may show evidence of an ancient volcanic eruption, which would be very exciting. So these are top up arrows. So the top of the core is here, and we melt top to bottom. And that way we can connect all the segments of ice, because they're in 1 meter segments, and create a long record. Minus 20 C. Not that much colder than a typical winter day in Maine, but still cold enough to suit up. I'm prepping the cores to melt, so I need to clean the ends of the cores. There might be some dust or particles that have just sort of stuck on the ends. So I scrape those off and get the ice into its core tray. These are ceramic blades, so they should not contaminate the chemistry of the core, and we clean them every day. Everything in the ice core world is very sensitive, because these are pristine records of ancient atmospheric chemistry, and we have to treat them that way.
I mean, I'm helping Bess track volcanic eruptions in an Antarctic ice core that spans back to 2,300 years. I mean, where else am I going to get an experience like that?
2.5 centimeters a minute. So we actually had a really interesting conversation out in West Antarctica. The fact that we're taking about 2 miles of ice and slowly drilling it over the course of 3 years, and then melting it all, and then analyzing it all. It's such a huge project that you can't really see it all at once. It's like you have to walk the distance of 2 miles to understand how much ice there is. It's just astonishing to think about what was happening in the world at that time, and the fact that this ice records the snow that fell at that time in Antarctica.
So the reason why we collect ice cores is that they're a really fantastic archive of climate. So every year we get snow that's falling, and the snow collects a lot of aerosols and the contents of the atmosphere. So we can look at, for example, what temperature was like, how much dust and aerosols and impurities there were in the air. And we actually get a collection of the air itself. So air slowly gets trapped in the snow as little bubbles. And in the system here, we can actually open up those bubbles and measure what the atmosphere was like in the past. We go to Greenland and we drill ice cores every summertime, so when it's warm and when it's light, so usually between April and August. And then once the ice is here in Copenhagen, then we can cut it up into different sticks and subsections for different types of analysis. This is our working freezer, and this is where we prepare the ice samples. So we have a bandsaw here that we use for cutting up the samples into pieces, nice and square, and we also have some ceramic knives for just doing the final cleaning on the edges.
Det vigtigste er, at vi får rene prøver. Og det er derfor, man vil hellere skære en millimeter af, for det er oftest ikke mere end på millimeter. Og så bliver det helt gode prøver. Det er svært at vurdere. Er det lige nu?
When we're preparing the ice, the most important thing is to remember which way is up. Because when you've once the ice has been drilled, then once it's on the table, you don't know which way is up or down, and you always want climate to go in the same direction. So that's why we put arrows on every single piece, so we always know which way is up. And we also put an arrow on the wall, so we know which way the pieces should go when they're on the table and in the room. So one of the analyses that we do here is this continuous flow analysis, where we cut the ice into a long stick, a square, and as you see in the freezer, then we can prepare the ice and put it into a frame and then it can be melted here continuously, section by section. Okay, so this is the melt head that we use to melt the ice cores, and you can see that it has this trench around the outside and then a raised central section. And the idea of the melt head here is that we put the ice on the center, and it sits over this little dividing bridge, and this separates the outer section of the ice, which is contaminated, with the inner section, which is clean. Today we're looking at, we're melting 25 meters of ice, and we're looking at what the climate was like 200 years ago. So the measurements we do here are basically for two purposes. One is to understand how climate is changing by looking at individual components such as dust, sea salts, forest fires, soil activity, and see how quickly these changes and how these changes happen over time. We also measure methane, which is an important greenhouse gas, and by combining these measurements we can look at how quickly climate has changed in the past, how climate was like in the Ice Age compared to now, and understand more generally what's happening with the world nowadays.
The only source of air which tells us about the composition of the atmosphere before, say, the 1950s, is polar ice. Well, we can measure the atmosphere directly from outside or baseline stations like Cape Grim, for example, or in the Antarctic, but that only gives us the recent picture of the atmosphere. So if you want to go back in time to before the last few decades, we have to rely on the polar ice sheets, which have been taking up air over thousands of years, sitting there waiting to be drilled and analysed. Our records go back about 3,000 years. You can go much further back in the Antarctic ice, you can go back almost 1 million years. Our focus, though, has been on the period of the industrialisation and moving back to, let's say, a few centuries or even a few thousand years. That lets us know what the natural background was like and how that changed as we started to emit gases into the atmosphere. It's a wonderful archive, and it's one which is providing some of the best information about the atmosphere over the last few centuries. We have a new atmosphere. We have an atmosphere which is elevated in some of these compounds which keep heat in the atmosphere, so the climate warming gases. We've seen large increases in all of those gases. As well as knowing about their increases, we can actually attribute the causes of those changes. Together we can say, well, a lot of the CO2 increases come from a combination of fossil fuels and from land clearing, from clearing of forests.